Almost every material expands when heated and contracts when cooled. But there is one common substance that does not follow this rule: water. It doesn't follow the rule of thermal expansion. That is the reason life exists on Earth. In general, every substance, solid, liquid, or gas, is made of tiny particles that are always in motion. When we cool a substance, the motion of these particles slows down. As a result, they come closer together and the substance contracts. Even water does the same thing at first. If we take water at a room temperature, say around 25 degrees Celsius, and start cooling it, we will notice as the temperature drops, its volume decreases and water contracts, exactly as we expect. But once it reaches 4 degrees Celsius, it no longer shrinks, and in fact, it starts expanding. Its volume actually increases when we further cool it. This is not what we expect, and that is why it is also called the anomalous expansion of water. Anomalous just means unusual, different, or not normal. Think about it. The number of water molecules stays exactly the same whether it's at 25 degrees Celsius or cooled down to 4 degrees Celsius. They are just packed a little closer together as it gets colder. The same amount of molecules now occupy a smaller volume, so the density of water increases, means it's getting heavier per volume. The increase in density continues until the temperature reaches 4 degrees Celsius. However, when the temperature falls below 4 degrees Celsius, water begins to expand. The molecules start moving further apart, meaning the same number of molecules now occupy a larger volume. As a result, density of water begins to decrease. That is why water is most dense and heaviest at exactly 4 degrees Celsius. But the story doesn't end there. If we keep cooling it even further, it doesn't remain a liquid forever. At 0 degrees Celsius, liquid water freezes and turns into solid ice. And suddenly and surprisingly, it expands a whole lot more, taking up about 9% more space. That means the same amount of mass now occupies a larger volume. So ice ends up with lower density than liquid water. That means ice is less dense than the liquid water it came from. And that is the reason why ice floats on water. Anything that is heavier sinks and lighter floats. This simple fact has massive consequences in nature. In winter, as air temperature drops, the surface water of lake or pond cools first. As it cools down toward 4 degrees Celsius, it becomes denser and sinks to the bottom. Warmer, less dense water from the below rises to the surface and cools in turn. This circulation continues until most of the water in the lake reaches about 4 degrees Celsius. Beyond this point, the surface water becomes lighter as it cools further, so it stays on top. When the temperature reaches 0 degrees Celsius, the top layer freezes into ice. And because ice floats, that floating ice acts like a blanket, insulating the water below. So the deeper water stays liquid, close to 4 degrees Celsius, allowing aquatic life to survive through winter. If water behaved like most other substances, getting denser all the way to freezing, this would never happen. Lakes would freeze from the bottom up, layer by layer, turning solid. And every winter, life in those waters would simply end. But this raises a deeper question. Why does water behave this way at all? Why does it stop getting denser below 4 degrees Celsius? And why does it expand so dramatically when it freezes? To answer that, we have to stop looking at water as a continuous liquid. We have to zoom in all the way down to the level of individual water molecules. A single water molecule is surprisingly simple. It consists of one oxygen atom bonded with two hydrogen atoms. The oxygen is more electronegative, meaning it pulls the shared electrons closer to itself. That gives the oxygen end a slightly negative charge and the hydrogens a slightly positive charge. It's polar, like a magnet. This polarity lets the negative oxygen of one molecule attract the positive hydrogen of another. This weak attraction is called a hydrogen bond. Individually, these bonds are short lived and weaker than the main bonds in the molecule. At higher temperatures, water molecules have more kinetic energy. They move faster, collide more violently, and constantly pull away from one another. In this state, hydrogen bonds still form, but they break almost as quickly as they appear. As the temperature drops below 4 degrees Celsius, the motion of the molecules slows down. Hydrogen bonds begin to last longer and start to dominate the arrangement of molecules. They organize water molecules into a structure that occupy more space but is energetically more stable. That is why water expands as it cooled below 4 degrees Celsius. When water finally reaches 0 degrees Celsius, it undergoes a phase change and freezes into ice. At this point, the hydrogen bonded arrangement becomes fixed. The molecules lock into a rigid, open crystal structure, like a 3D honeycomb. Because this structure contains large open spaces, ice occupies significantly more volume than the same amount of liquid water. That is why water expands suddenly on freezing, and why solid ice has much lower density than liquid water. So, water's strange behavior is not random and it is not magic. It is the result of delicate balance between molecular motion and hydrogen bonding. Above 4 degrees Celsius, motion dominates and water behaves normally. Below 4 degrees Celsius, hydrogen bonds shape an open structure, forcing water to expand. And at 0 degrees Celsius, that structure locks in permanently as ice. This isn't just a microscopic detail, it shows up dramatically in everyday life. If you live in a cold climate, you have likely heard the destructive side of this: water pipes bursting in the dead of winter. As the water trapped inside freezes, it expands with such immense pressure that it splits solid metal or plastic wide open. Next time you drop an ice cube into your lemonade, take a moment to appreciate the miracle in your glass. Even though that ice is a solid, it refuses to sink like a stone. Ice is lighter than the liquid water it came from, so it rises and floats at the surface. This simple fact quietly turns massive icebergs into silent drifters on the ocean. In the early 20th century, the Titanic, a ship made of steel, you might have also seen the movie, struck such a floating iceberg. One solid sank, the other floated. Not because of size or strength, but because ice, no matter how massive, is still less dense than liquid water. So, water's anomalous expansion doesn't just make ice float, it literally shapes history. If the ice had been heavier and sank, our oceans would eventually freeze from the bottom up. Once frozen, they would never fully melt and the earth would be a frozen desert, a silent ball of ice spinning through the space, where life could barely begin. But the story of the rebel molecule doesn't end at our atmosphere. When we look up at the stars, we see ice everywhere on wandering comets, ancient asteroids, and the moons of giant planets. And because we understand how water behaves, we suspect that beneath those frozen surfaces of Jupiter's moon, Europa, or Saturn's moon, Enceladus, lie deep liquid oceans, kept alive by the same strange rules you see in a winter pond or a glass of lemonade. Perhaps in the far reaches of the universe, under extreme pressures we can barely imagine, there are different forms of ice, denser exotic ice, that sink to the bottom. But here on Earth, under ordinary conditions, water's refusal to behave normally might have been one of the most important accidents of nature that kick-started life on Earth and is likely doing the same elsewhere across the galaxy. If this video helped you see water or even ice a little differently, let me know in the comments. I would love to hear what surprised you the most, or where you have seen this strange behavior play out in real life. And if you know someone who enjoys understanding how the world works, someone who likes asking why, feel free to share it with them. Also, if you ever feel like supporting the channel, there is a Patreon link below. Don't forget to subscribe because this is just one chapter. We are only beginning our journey into the physics of heat, temperature, and the quiet rules that shape our universe. Until next time, stay curious and stay wow.